In the last lecture, we looked at pure cubic fields and how to find rings of integers of pure cubic fields. And we also looked at one example where we could find a unit of infinite order in a pure cubic field. And I said I would do biquadratic extensions next time, but let me go back to quadratic extensions first, because it makes more sense to do it this way. So, in today's lecture we will look at real quadratic number fields. We will not study the class group as such in general, but the the unit group in real quadratic fields. So, let k equal q square root of d, where d is a natural number and it is square free. Okay. Then we know that, so this is by Dirichlet's unit theorem, that the rank Z rank of OK cross modulo torsion is 1. So, this is a group of infinite order OK cross. So, question is, how do we find all elements of OK cross? Right. So, that is the question. Of course, if you look at torsion of OK cross, then this is precisely plus or minus 1, as k is contained in real numbers. Right. The torsion is necessarily roots of unity, and the only roots of unity that are real are plus and minus 1, and plus and minus 1 are in OK. So, the question is, how do we find other an element of infinite order? So, we want x and y in z, let us say such that x squared minus dy squared equals 1, right. Yeah, or this need not always right. So, of course, this is kind of this will give you a unit, right, this will give you a unit, but we also know that the basis of OK, the z basis of OK depends on what d is modulo 4. Okay. All right. So, so today we are going to solve. So, today we solve x squared minus dy squared equals 1 for x and y in z. So, that will give us this thing is called Pell's equation. Okay, this is called Pell's equation, and one way to solve this is using what is called continued fraction. So, you look at the continued fraction expression for square root of d and use the use this continued fraction truncated at certain point to find x and y. Okay. So, that is one way of doing this thing, but we are going to look at some other way of doing this, which is perhaps not as fast as finding using continued fractions, but it is closer to our course. Okay. All right. So, right. So, one thing, an observation, if x squared minus dy squared equals 1, then we know that norm from k to q of x plus or minus, does not matter which one I take, this is equal to plus minus 1. Sorry, this is equal to plus 1. What am I saying? Is equal to 1, right? Okay. So, by the way, I should say that this is sufficient to have a unit, but it's not necessary, because unit could also have norm minus 1, right. And as I said, x and y need not always be an integer for things to be in OK. All right. So, in any case, we are going to solve this particular equations. We are going to use the sufficient condition to find some solutions, and then hopefully we will have a way to patch these things together to get all solutions. Okay. All right. So, once you write it like this, it is kind of clear that the following happens. So, you can get, if we have one solution x1 minus x1 square minus dy1 square equals 1, then yeah, so whenever I say a solution, I mean non-trivial solution, then we can generate infinitely many solutions. Okay, and how do we do that? Well, we know that norm from k to q of x1 minus square root of dy1 is equal to 1, and hence we also know that norm from k to q of x1 minus square root of dy1 to the power k is also equal to 1 for all natural numbers k. Right. So, in particular, we can write x1 minus square root of dy1 to the k. This we can put all these terms together and write it like this, right, for xk and yk inside z, right, and then this becomes so then xk squared minus dyk squared is also 1. Okay. And y is yeah, so I said this gives you infinitely many solutions, but it may happen that you get repetition after some point, right. So, why do we get distinct solutions? So, why are all these solutions distinct? Well, if not, if there exists k1 not equal to k2 such that x1 minus square root of dy1 to the k1 is equal to x1 minus square root of dy1 to the k2, then x1 minus square root of dy1 k2 minus k1 is equal to 1. Say k2 is bigger than k1 for sake of notation, then x1 minus square root of dy1 is a root of unity. And we are not working with we are starting with a non-trivial solution. So, we do not want a root of unity, right. So, that tells you that if you have one solution, you can get infinitely many solutions. Okay. So, what have we done? Let me kind of take a step back and tell you what we have done. So, OK cross modulo plus minus 1, this is isomorphic to z, right. There is a generator of this. All I am saying is that if you take some non-trivial element in here, it generates a non-trivial subgroup of z, right. So, if x1 minus square root of dy1 is a non-trivial element in OK cross modulo plus minus 1, then we get a subgroup of OK cross modulo plus minus 1 isomorphic to Z. Okay. So, we get a subgroup of this. We do not get the, we need not get the whole thing. We would like to find everything. We would like to get an non-trivial element that generates the whole group Z, right. But anyway, so we will come to that in a moment, but let me give you some examples and show you how this is quite powerful. So, I want to solve something like x squared minus square root of 2 y squared equals 1. So, I can find one solution for this just by inspection, which is x is equal to 3 and y is equal to 2, right. So, I get 3 squared minus yeah, I think I made a mistake a few no. So, here I was writing it correctly. This is the first, this I mean I want to solve this with 2, not square root of 2, right. I mean this is same as saying norm from q square root of 2 to q of x minus square root of 2y is equal to 1. Okay. So, 2 into 4 right, this is 1. So, I can look at 3 minus square root 2 square root of 2 square, and if you do the calculation, this is 9 minus 12 square root of 2 plus 8. So, this is 17. Yeah, sorry, I would like to take plus here. So, I end up with all positive things again, does not matter. So, this is another solution. So, you see that 17 square minus 2 times 12 square is also 1, and you can keep going. You can write 3 plus 2 square root of 2 cubed. This turns out to be, so maybe I will do this particular one explicitly for you. So, this is 3 cubed minus 3 into 3 square into 2 square root of 2, sorry, not minus, plus 3 into 3 into square of this. So, 4 times 2 plus cube of this. So, 8 into 2, 16 square root of 2. So, this is 27 plus 9 into 8 is 72 plus 54 plus 16 square root of 2. So, this is 99 plus 70 square root of 2, right. So, this is another solution. So, 99 square minus 2 times 70 square is equal to 1. And as I said, you can keep going and you can in fact generate very large solutions this way to the 4. This is 577 plus 408 into square root of 2, and 3 plus 2 square root of 2 to the 5. This is 3363 plus 2378 square root of 2. So, two things to notice. Of course, you are getting different solutions at each stage, but also these coefficients are getting much larger, right. So, you would not have found this just by pure inspection, and if you just went looking through all integers, then that would be a very cumbersome process, right, where it would take a long time to reach 3000 and 2000. You would have to you would have to do many cases. Okay, we can look at another example. So, I want to solve x square minus 3y squared equals 1. Then again you can just look at this just by inspection. You see that the x equal to 2 and y equal to 1 is a solution, right. And so, I can look at 2 minus plus square root of 3 square, this is 7 plus 4 square root of 3, 2 plus square root of 3 cube, this is 26 plus 15 square root of 3 and so on. Okay. Now, not only that, you can just not by taking powers, but you can also add, you can also multiply two solutions to get another solution. So, if x1 y1 and x2 y2 are solutions to x square minus dy square equals 1, then you take x1 minus y1 square root of d, x2 minus y2 square root of d, and you write it as x3 minus I mean you can put minus or plus, does not matter. Let me put plus here. Then x3 y3 is also a solution, and I am going to leave this as an exercise. You just have to take norm, and the fact is that norm is multiplicative. Okay, so what is the upshot of all this? The upshot of all this is x square minus dy square equal to 1 has infinitely many solutions. So, if this has a solution, has a non-trivial solution, then it has infinitely many non-trivial solutions. Okay. All right. So, the question would be, is there a non-trivial solution, and how do we find one? Okay. So, the question would be, is there a non-trivial solution So, if yes, how do we find it? And how do we find all solutions? Right, as before, as in the first lecture in this course, I said these are the fundamental things that one needs to answer, that sort of number theory aims to answer. These are the fundamental questions that number theory aims to answer. Okay, so we can answer the first question straight away. So, one has answered yes. And why is that? Well, we know that rank of OK cross modulo plus minus 1 is equal to 1. Hence, there exists a unit, let us say x plus square root of dy in OK, right. And so, norm of this thing x plus square root of dy, this is 1 or minus 1, right. We are not sure which one it would be. Nevertheless, if you take norm of x plus square root of dy whole square, this will be 1, and that will give you your solution, right. So, that is so hence the answer to the first question is yes. And so, how do we find all of them, right. So, that is kind of the second, how do we find even one solution, and then how do we find all such solutions. Okay. Right. So, here is a lemma. If x square minus dy square equals 1, x and y in z, then, and I also assume that x plus square root of dy is bigger than 1, then x is bigger than or equal to 2 and y is bigger than or equal to 1. Right. So, yeah, so this is always the case, and it is kind of very easy to prove, but let me prove it anyway. And why can we, I mean, this is not a serious restriction that x plus square root of dy is bigger than 1, because I can assume that both x and y are positive, right, because if x is a solution, x and y is a solution, then so is plus minus x and plus minus y. So, in particular I can always assume that x and y are both positive, and hence this thing will hold. Yeah, okay. So, how do I prove this? Yeah, by the way, I am not right. I said I can assume that both x and y are positive, but I am not assuming that in this particular state. It is not a hypothesis that x and y are both positive. It can happen that x is positive and y is negative, and I am getting this bigger than 1. The conclusion tells me that it cannot happen, but a priori it can happen that x is positive, y is negative, or x is negative, y is positive, and that is why I am getting this real number to be bigger than 1. So, the thing to notice is that this thing is inside real numbers, right. I could not do this for complex numbers if d were negative. Okay. So, how do I do this? Right. Okay. So, what happens if I look at x minus square root of dy? This is 1 over x plus square root of dy, just because norm of x plus square root of dy is 1, and so this thing will be less than 1. This is by our hypothesis. So, what we have is x plus square root of dy is bigger than 1, which in turn is bigger than this quantity, and yeah, and because 1 plus square root of dy is positive, its reciprocal is also positive. So, we have this, right, and so you see that yes. So, in particular you see that x plus square root of dy is bigger than x minus square root of dy, and so if I just rearrange this, I get 2 times y times square root of d is bigger than 0, and the only way this can happen is if y is bigger than 0, which means that it is, as it is an integer, it is bigger than or equal to 1. All right, sorry. Okay, and now x square is equal to 1 plus dy square, and these are both bigger than, so d is bigger than 1, and so this is bigger than, right, I mean at least 3, and the smallest square bigger than or equal to 3 is 4. So, x is bigger than or equal to 2, right. Okay. Yeah, so if you change the sign, if x and y are not positive, both positive, then a unit like this will have as a real number will be less than 1, right. So, that is kind of a very strong restriction, yeah, on the solution. Now, I will write down another lemma which again gives a very strong restriction on the solutions. So, suppose x square minus dy square is equal to 1, and this is also equal to a square minus db square, x, y, a, b, they are all integers bigger than equal to 0, let us say. Then the following are equivalent. What are the following? Well, if I have x plus square root of dy is bigger than a plus square root of db, right. So, this inequality, I mean a priori this inequality does not have anything to do with it need not have the thing that x is bigger than a and y is bigger than b, but that is what happens, x is bigger than a and y is bigger than b, and even better what you have is x is bigger than a or y is bigger than b. So, any one of those inequalities is enough to get what you want. So, it is clear 3 implies 2 implies 1 is clear, right. And so, we want the other way around, we want to assume that 1 should imply 2 and 2 should imply 3. Yeah, right. And a and b are both bigger than 0, hence yeah, sorry, bigger than or equal to 0. So, then so what happens if a is equal to 0? So, if a is equal to 0, then minus db square is equal to 0, which means that b is equal to 0, but then a square minus db square is 0, which is not equal to 1. So, a contradiction, which means that a is not equal to 0, and so a is bigger than or equal to 1, right. And similarly, x is bigger than or equal to 1, right. And now we are kind of in a better situation. What we have is a plus square root of d times b is less than x plus square root of d times y, which means that 1 over a plus square root of d times b is greater than 1 over x plus square root of dy. But what are these? These are a minus square root of d times b and x minus square root of d times y, right. And now you add these inequalities, you get a plus x plus b minus y square root of d is less than a plus x plus y minus b square root of d, and you rearrange this a little bit, you get y 2 times y minus b square root of d is bigger than 0, which means that y is bigger than b. And if you subtract these, so this is by adding the two inequalities, and by subtracting the two inequalities you would get the other way. So, we will finish this next time, because this shows that 1 implies 2, we still need to show that this shows that which way numbering go? Yeah, so this implies that 1 is same as 2, we need to show that 1 is also same as 3. So, we will finish this next time. Thank you.